We can classify the chemical properties of carbonyl compound in three categories. First category is nucleophilic addition reaction. Nucleophilic addition reaction. The second category is oxidation reduction reactions. Oxidation and reduction reaction. And third type of reaction which carbonyl compound can give, that are condensation reaction. So we will start from nucleophilic addition reaction. As we can understand, the carbonyl compound have double bond. That's why they can give which type of reaction, that is addition reaction. And they give nucleophilic addition reaction. It means at in first step, nucleophile attack on carbonyl carbon. The pi bond electron move toward oxygen atom. That's why oxygen atom acquire partial negative charge and carbon become partially positively charged. And nucleophile attack on carbonyl carbon. That is the first step, and that is a slow step. That's why that is rate determining step. In rate determining step, because nucleophile is attacking, that's why that reaction are known as nucleophilic addition reaction. In second step, the H plus ion attack on oxygen, or oxygen donate its lone pair to H plus ion. That's why we get the complete compound or as a product. So we can observe here the carbonyl group is sp2 hybridized. Carbon of carbonyl group is sp2 hybridized. That's why its shape is planar. So we can say nucleophile can attack from backward as well as from forward direction. So in product, our carbon convert into sp3 hybridize. So shape become tetrahedral. Now the main point is that if our nucleophile and the group A, group B all are different, then in that case our product may be optically active. So if our product is optically active, because nucleophile can attack from both sides, forward as well as backward, that's why we will get 50% dextrorotatory and 50% levorotatory substance mixture of 50% dextrorotatory and 50% levorotatory our product. So our product will be in the form of racemic mixture. So if product of nucleophilic addition reaction in carbonyl compound is optically active, then always we will get racemic mixture, because carbonyl compound is planar shape and carbon have sp2 hybridized, so nucleophile can attack from both side, forward as well as backward side. So that is the stereochemistry of product of nucleophilic addition reaction. According to reactivity, aldehydes are more reactive than ketone in nucleophilic addition reaction. Reactivity of carbonyl compound towards nucleophilic addition reaction depend on two factors. First factor is steric hindrance. So in aldehyde there is a H is attached to carbon. So we can say the atomic size of H is very small compared to two carbon atom which are present on ketone. Steric hindrance in ketone is more. That's why nucleophile will faster attack on carbonyl carbon of aldehyde. That's why aldehyde are more reactive toward nucleophilic substitution reaction. So first reactivity factor, the factor which affect the reactivity is steric reason. We can say steric factor. The second factor is electrophilicity. Electrophilicity of carbonyl carbon. Carbonyl carbon. The positive charge. Why nucleophile attack on carbonyl carbon? just because carbonyl carbon have positive charge. If the intensity of positive charge is increased, so nucleophile will attack faster. In the case of ketone, there are two alkyl group are attached at carbonyl carbon which have plus I effect. Due to plus I effect, they push the electron of sigma bond toward carbon. That's why they decrease the electrophilicity. They decrease the electrophilicity of carbonyl carbon. That's why reactivity of ketone is less than reactivity of aldehyde. Similarly, we can understand the propanol CH3 CH2 C double bond OH, that is more reactive to benzaldehyde. That is more reactive to benzaldehyde. There are again two reasons. First reason is that the phenyl ring is bulky. That's why nucleophile attacks slowly in the case of benzaldehyde. The second reason is that phenyl ring and carbonyl carbon have pi-pi conjugation. That's why when oxygen of carbonyl carbon accept the pi electron, then pi bond of benz or phenyl ring will shift towards carbon, and due to this the phenyl ring actually decrease the electrophilicity of carbonyl carbon. That's why nucleophile attacks slowly. That's why propanol or it is more reactive towards nucleophilic substitution, nucleophilic addition reaction compared to benzaldehyde. Now we are taking some examples of nucleophilic addition reactions or nucleophilic addition reaction. So first example is what happens when carbonyl compound react with HCl. This reaction occurs in the presence of base. So what is the reason we are taking here base? Because base means OH minus accept the H plus ion from HCN and produce Cn minus. So Cn minus is a good nucleophile compared to HCN. That's why we are taking base to produce good nucleophile Cn negative. Now this Cn negative means nucleophile. In first step, it attack on carbonyl carbon because when we shift the electron of pi bond toward oxygen, because oxygen is a more electronegative than carbon, so carbon acquire partial positive as well as oxygen acquire partial negative charge. So nucleophile means Cn negative attack on positively charged carbonyl carbon. So we will get this tetrahedral intermediate. Why we are getting tetrahedral intermediate? Because hybridization of carbon is now changed. Here hybridization is sp2, but in intermediate hybridization is sp3. Now it in second step it accept H plus ion, means O minus will donate its electron to H plus ion and we will get our final product, that is the cyanohydrin. So that is our cyanohydrin. So cyanohydrin actually are very important synthetic intermediate. Why cyanohydrin are so important? You can understand like that. CN group cyanide. If we do partial hydrolysis of cyanide, then cyanide group gets converted into CuNH2 means amide. If we do complete hydrolysis, complete acidic hydrolysis, in that case cyanide group can convert into carboxylic acid. Similarly, we can convert cyanide into amine also if we do the reduction of cyanide using LiLH4 or any other reducing agent. Then cyanide gets converted into amine, means we will get CH2NH2. So we can say cyanide can convert into amide as well as carboxylic acid COOH as well as amine. That's why this cyanohydrin is a very good intermediate. Now another example of nucleophilic addition reaction, addition of sodium hydrogen sulfide. What is the formula of sodium hydrogen sulfide? That is NaHSO3. NaHSO3. So that is a formula for sodium hydrogen sulfide. So similarly, sodium hydrogen sulfide means there is SO attack of sodium hydrogen sulfide, and we will get bisulfide addition compound, that is crystalline nature. Next one is addition of Grignard reagent. Yes, we can add Grignard reagent also. Means if we have carbonyl compound like C double bond O and we have Grignard reagent like RMgX. So electron of pi bond will be shift towards oxygen atom. So oxygen atom will acquire partial negative charge and carbon will acquire partial positive charge, and the bond of R and Mg will break, and the electron will shift towards R, means carbon, because carbon is more electronegative than magnesium. So here magnesium will acquire partial positive charge. Ultimately we will get an intermediate like OMgX, and R will attach to carbon. Now if we do the hydrolysis, so that bond will be break and H, and here will be attached OH. So our product is RCOH plus MgXOH. So we can say when aldehyde or ketone reacts with Grignard reagents, then we get alcohols. If formaldehyde react with Grignard reagent, then our product is 1 degree alcohol. If any other aldehyde react with Grignard reagent, then we will get 2 degree alcohol, and when ketone react with Grignard reagent, then we will get 3 degree alcohol. Next one is addition of alcohol. Similarly, alcohol can be react with aldehyde or ketone, and we will get hemiacetal or hemiketal. Why it's called hemi? Because one OR is attached to carbon. If there is also OR, means alkoxy group is attached, then that is called acetal. Why we are taking HCl gas? Just because dry HCl gas protonate the oxygen of this alcohol. So dry HCl protonate the oxygen of carbonyl compound, and that's why therefore increase the electrophilicity of carbonyl, so facilitating the nucleophilic addition reaction. If we are using ethylene glycol, that is ethylene glycol, then same reaction will occur and we will get cyclic compound, that is called ethylene glycol ketal. Then addition of ammonia and its derivative. So ammonia and its derivative we can represent by NH2Z. Now what is Z? Apart from one NH2, everything is Z. For example, in ammonia, when we are talking about ammonia, now what is Z here? In the case of ammonia, Z is H. But if we are talking about hydroxylamine, that is also ammonia derivative. So what is Z here? Here Z is OH. So if we are taking ammonia or ammonia derivative, means NH2Z, then we will get our compound like that. Similarly, that is an example of nucleophilic addition elimination reaction. Here the step is addition. In second step there is elimination. So these are called nucleophilic addition elimination reaction. The equilibrium shift towards product side, because as soon as this intermediate is formed, it gets converted into this final product by elimination of one molecule of H2O. So if Z is H, then reagent is ammonia. If Z is R, then amine. Z is OH, then that is called hydroxylamine. How? If we are making the structure of ammonia, means apart from NH2 there is only H is present, that is Z. 1 degree amine, RNH2. What is here? Z is R, and hydroxylamine structure of hydroxylamine is NH2OH. So what is Z here? OH. What is hydrazine? Structure of hydrazine is NH2NH2. So what is Z here? 1NH2. Similarly, phenylhydrazine. The structure of phenylhydrazine is like NH2, NH, and one phenyl ring is attached. So apart from this NH2, the whole that species or whole part is called as Z. So that is a Z. Similarly, 2,4-dinitrophenylhydrazine. That is very important. When we make 2,4-diphenylhydrazine, when we react 2,4-dinitrophenylhydrazine from carbonyl compound, either aldehyde or ketone, they will form 2,4-dinitrophenylhydrazone, and it will give yellowish white precipitate. That's why this is called 2,4-DNP test. 2,4-DNP test. The test is given by positive aldehyde as well as by ketone. So these all are the nucleophilic addition elimination reaction of carbonyl compound. Similarly, when semi-carbazide, what is the structure of semi-carbazide? The structure is NH2, NH, C double bond O, NH2. When semi-carbazide react with aldehyde or ketone, it will form semi-carbazole. Here are 3 nitrogen atom having lone pair. So 3 can act as a nucleophile, but only one nitrogen atom act as a nucleophile, and that is the nitrogen. Only that nitrogen act as a nucleophile just because these lone pair and these lone pair are in conjugation. With the pi bond. That's why this nitrogen atom cannot donate its electron. This nitrogen atom cannot donate its electron. That's why this nitrogen atom cannot act as a nucleophile. This nitrogen atom again cannot act as a nucleophile. Only this nitrogen atom can act as a nucleophile. That's why only this can donate its electron. Another reactions of carbonyl compound are reduction. So we all know aldehyde and ketones when react with NaBH4 or LiAlH4, then they gets converted into alcohol. If they react with reducing agent like LiAlH4, NaBH4 sodium borohydride, they gets converted into alcohol. Aldehyde gets converted into 1 degree alcohol and ketone gets converted into 2 degree alcohol. Next one is reduction of 2 hydrocarbon. So that is, we can say, Clemenson reduction. There are 2 important reduction. First one is Clemenson reduction and second one is, so first important is Clemenson reduction. That one is Clemenson reduction. That is important. And second one is Wolff-Kishner reduction. Now what is Clemenson reduction? In Clemenson reduction, our carbonyl compound react with zinc amalgam and HCl, and that's why it gets reduced into CH2. So the reagent zinc amalgam, ZnHg and HCl. We have to remember this reagent is the reagent of Clemenson reduction. This is the reagent of Clemenson reduction. And similarly carbonyl get converted into CH2 by another reagent, that is NH2 means hydrazine, then QH in second step, QH in the presence of ethylene glycol. If we heat, then carbonyl compound can also gets converted into CH2. So that is an example of Wolff-Kishner reduction. Now what is the important part is that because we are using HCl, in Clemmensen reduction. That's why Clemmensen reduction cannot be used for acid sensitive groups. And in Wolff-Kishner reduction we are using KOH, means that is a base. So Wolff-Kishner reduction cannot be used in base sensitive reactants. For example, if I have CH3 C double bond O, CH2 O, CH3, and I want to just convert this CO group into CH2, I don't want to impact on this ether group. So we cannot use here Clemmensen reduction, because Clemmensen reduction also attack on this ether group. That's why we have to use Wolff-Kishner reduction in this reaction. We cannot use Clemmensen reduction. If we want to if we want that this ether group is remain intact, then we have to use Wolff-Kishner reduction, because there is a acid sensitive group, that is ether is present. Another one is oxidation reduction reactions. Now we know the aldehydes easily oxidize into carboxylic acid, but ketone cannot easily oxidize into carboxylic acid. But if we use vigorous conditions like very hot acidic concentrated KMnO4, then ketone can also gets converted into carboxylic acid. So what happen if we are using RCH2 C double bond O like CH3, and we are using vigorous conditions, then what happen, this ketone can also convert into carboxylic acid. So how this will happen, it will happen according to Popov rule. Now what is Popov rule? According to Popov rule, we have to break this bond, means carbonyl group will remain with lesser carbon. So we will get RCOH plus CH3 COOH. This carbonyl group will remain with lesser carbon alkyl group. That is called Popov rule. But it can be possible only when we are using strong oxidizing agent, very strong oxidizing agent like hot concentrated uh, acidic KMnO4. In normal conditions, ketone cannot be oxidized. That's why these oxidizing properties or oxidation nature we can use as a distinguished test for aldehyde and ketone. So we can use Tolen reagent, Fehling reagent, Benedict reagent, Schiff reagent. Actually these are mild oxidizing agent. These all are mild oxidizing agent. So they oxidize only aldehyde. They does not oxidize ketone. That's why they give positive test with aldehyde but negative test with ketone. So first of all there is Tolen test. What is Tolen test? When we warm the aldehyde with freshly prepared ammonical silver nitrate solution. Now this ammonical silver nitrate solution is known as Tolen's reagent. Then we get silver mirror. at the bottom of our test tube due to formation of silver metal. That's why we can say the means that sample is aldehyde, means only aldehyde give this Toland test positive. Ketone cannot give this Toland test positive. As well as Fehling test. In Fehling test, we use Fehling solution A and Fehling solution B. So Fehling solution A is aqueous copper sulfate and Fehling solution B is alkaline sodium potassium tartrate, that is also called Rochelle salt. We have to prepare fresh Fehling solution by mixing of Fehling solution A and Fehling solution B. Now in Fehling solution, copper are present in Cu plus 2 state and they gets converted into Cu plus 1 state. So Cu plus 2 gets converted into Cu2O and it will give reddish brown precipitate. So this reddish brown precipitate only produced by aldehydes. Ketone cannot give this reddish brown precipitate because we are using Fehling reagent. That Fehling reagent again mild oxidizing agent. They can oxidize to only and only aldehyde. They cannot oxidize ketone. Again is oxidation of methyl ketone by haloform reaction. The haloform reaction can only give by those aldehyde or ketone which can give ketomethyl group. Means carbonyl group should directly attach to methyl group. They can also haloform reaction can also give by those alcohols which after oxidation gets converted into ketomethyl group. So that alcohol can also give positive haloform reaction. In haloform reaction there is this CS3 group. This CS3 group gets converted into haloform. Haloform means if we are using NaOX, means if we are using NaOI, then we will get iodoform and brown precipitate of iodoform will form and we can identify the ketomethyl group. So we can say haloform reaction can given by those aldehyde or ketones which have ketomethyl group or those alcohol which after oxidation can give ketomethyl group. So these are the oxidation and reduction reactions. Thank you.